Hello again. Let's see if we can do another short video, this time on fission and fusion, which again we touched on in physical science, and we're just really recapping our knowledge. We've talked about this graph before, where we've got mass number and binding energy, and how we've got this plateau up here of most tightly bound or most stable nucleuses, and how these guys want to go by fission and these lighter elements want to undergo fusion. And what they've also shown here is because this is binding energy per nuclear particle, nucleon in MeVs, when an atom goes from here up to here through fusion, because you're changing the binding energy, this is the yield from nuclear fusion. Whereas if you go from here to here, that would be the yield, because we're getting a change in the binding energy, and so this is per nucleon, and this would be the yield from fission. We'll have a couple of questions in your workbook that will hopefully sort that out. Okay, but that's we're looking at two sides of this diagram. Now in fission, it's when you have a heavy, for example uranium or plutonium, heavy atom made up of lots of nucleons and protons, splits into two nuclei roughly the same size, plus several neutrons. They're kicked out or freed, basically, is another way of saying it. Now this is most often the result of neutron bombardment, but it can happen naturally. And there are neutrons naturally around, but we also do it within reactors and in atomic weapons. And this is another example. There's uranium getting strontium and xenon, and three neutrons, and now these neutrons could collide with another parent nucleus and develop a chain reaction. So the chain reaction is where, and this is an example, uranium-235 gets hit by a neutron, you're given off strontium and xenon, plus one neutron is lost, which is commonly lost, just doesn't interact with a uranium-235, but the other two neutrons collide with uranium, and so from one fission you get two fissions, and from two fissions you get four fissions, and so you get a growth in fissions. And if each of these fission events releases energy in terms of mass conversion from using E equals mc squared, you're generating, very soon you're generating a massive amount of energy very quickly. And on your OneNote there's a video on chain reaction. Now fusion, however, is when lighter elements join together to produce more stable, heavier elements. And here we have helium hitting nitrogen-14, and you're getting oxygen plus a proton given off, neutron bombarding nitrogen-14, and you can get carbon-14 as well. So it could be an alpha particle or a neutron fired at in this case, and so that's an example of fusion, where you're joining things together to produce something heavier. But there are a lot more other examples of fusion as well, which we'll talk about shortly. In fission reactors, basic design of a fission reactor, which is the type of reactors we have these days, because we don't have any fusion reactors, is you have your fuel rods, they're inside a chamber, you have control rods. Now these control rods are usually something like graphite, and they are neutron absorbers, because we'll see in a second. If these fuel rods, they're undergoing radioactive decay normally, and so they're producing lots of neutrons, and those neutrons can collide with other to produce other uranium, for example, or plutonium. And what these control rods do is they can be lowered, and they absorb some of the neutrons, and they can control the energy output from the fuel rods. Now in here you have some heavy water, and that water goes in, gets very hot obviously, and then goes into a heat exchanger, produces steam, and steam goes into a turbine to generate electricity. Basically that's how they work. There's pumps and things, and then there's a containment vessel which has to be able to withstand all that force and heat. Excuse me. if something goes wrong. So they're the basic design, very simplified, but are actually very complicated machines. Now, what's the difference between a bomb and a controlled reaction like we have in a fission nuclear reactor? Well, here we go again. We're bombarding with neutron, producing 3 neutrons and the fission products. Now, in a controlled reaction, neutrons are absorbed, so that's where the control rods go in, and so you might just get one fission, then another fission, then another fission, and each of these produces a bundle of energy, and basically the reaction is controlled, and you control how many neutrons are absorbed by lowering or raising the control rods. Whereas in a chain reaction, that doesn't occur. It just keeps going on and on and on. Now, how do they make a bomb? Well, these two that we're going to show here are two of the very earliest bombs, so very simple designs. Basically, what you're getting is very much pure uranium-235. In this case, it's uranium-238, and this one has a plutonium sphere, so slightly different. But these two orange masses, when they're combined, they reach what is called a critical mass. And a critical mass is when the purity of a radioactive isotope is such that if you have a certain amount, it's producing enough neutrons to sustain within itself a chain reaction. And that chain reaction will then go out of control, just go boom. So these two masses by themselves are producing lots of neutrons, but there's not a density of neutrons to actually occur as a chain reaction. And so what happens in this bomb is these two masses now would then become a critical mass when they're combined. So this cone spheres into this, probably also has a degree of compression related to it, because that's how to get the critical mass, the density of neutrons, by squeezing out all that empty space between atoms. And so then it undergoes a chain reaction and you have your bomb. This one's a little bit different in that it uses conventional explosives. First of all, this shell of conventional explosives are designed to produce a shock wave that goes in. Also has one that goes out, but it's the one that's in. It's like a focused shock wave, and that shock wave compresses the uranium-238, so the 238 goes critical, reaches a critical mass and explodes, and that produces a secondary shock wave which then causes the plutonium to be compressed to such a stage for it to actually sustain a chain reaction. And so this is a plutonium bomb, but which uses uranium as a catalyst, sort of. Alright, so there's two examples of chain reactions. Now, if we duck back to fusion, what do we mean by fusion? We used a couple of examples, but in terms of nuclear fusion, people talking about making nuclear reactors, this is the main type of reactions that they're talking about harnessing in nuclear fusion reactors. And that is where where's my thing gone? There we are. You have two isotopes of hydrogen, tritium and deuterium, and you force them together, and that produces a helium and a neutron. And that releases a massive amount of energy because the masses do not correspond, and so mass gets converted to energy using E equals mc squared, and hence the energy given off. And the neutron is pretty harmless, that just whizzes away and doesn't do anything, because the neutron is not going to cause much radioactivity. It will cause some incidental radioactivity through its bombardment, but that's relatively short-lived. And so this is the process that they're all trying to use. Now, deuterium and tritium, easy to get. They occur naturally, and if you go into seawater and refine it and use some chemical processes, there's virtually limitless deuterium and tritium, and these generators can actually be used to generate their own, if necessary, by using the neutron that's excess to requirements. So in the fusion, and the output is only helium, which is pretty harmless. There's actually a demand for helium, and so that because it's always leaking out into space, and so if we could produce more helium, it wouldn't really be a problem. And the basic process of doing this, now this is what occurs in the sun, and so they're trying to mimic what's happening in the sun. And so you imagine how hot and dense the sun is because of its gravity and due to its size. That's what we've got to mimic. And so the plan is to heat up a plasma up to 100 million degrees Celsius. That plasma would be too hot for any containment vessel, and so you have to actually levitate it by using magnetic and electric fields, and so the plasma can't touch anything, and they make it basically a donut shape. A lot of this is going to be in the videos that you watch in OneNote, and experts far superior to me can explain it, but I'll just quickly talk through it. And this produces the heat which runs the steam turbines much the same. Now these neutrons will really only cause a little bit of the materials within the reactor to become radioactive, and the estimate of the radioactivity is only for 100 or so years, which is relatively short, because when they decommission a fission reactor, parts of the nuclear reactor there will be highly radioactive for tens if not hundreds of thousands of years. And that's one of the major problems with nuclear fission reactors. Whereas the fusion reactors, which haven't been built yet, but they are building the first commercial pilot one, and so it will be interesting to see how that's going to happen. So, and this was the first. This is Telemark, I think. There's a guy for scale, and this was the first test one, and it sustained fission for a fraction of a second, if not a couple of seconds, I think. And it was a major engineering feat just to get that to happen. And once they did, they said, well, this is possible, we can do it. They decided to upscale it, and they're going to make, or they're actually making a fusion reactor called ITER in Europe, and the videos will tell you more about that. But you can see that the plasma would be in here, and most of this is heat extraction plus being able to feed in fuel and take out the helium. So major engineering challenges. So there's a couple of videos on OneNote. Have a look at those. Pretty interesting, I think so. Certainly within your lifetime, fusion may well be out there and supplying a lot of electricity. So we've had that one. Now the ITER is going to be this size, and there's your person as a scale, so significantly upscaling it. Basically it's a prototype for industrial power generation using fusion, and so a lot of money's been spent on it, a lot of people employed, a lot of physicists and engineers, but it's really cutting edge stuff. And now they're not the only people trying to work on fusion. NIF, or the National Ignition Facility in America, they're trying to use lasers to initiate fusion, and there's a couple of videos again which explain it vastly superior to me. So there's a bit of competition. Most people would say that ITER or ITER is ahead of the NIF in terms of sustaining fusion and the likelihood of actually having a commercial reactor. This one is very much research, but still very interesting in terms of what they're thinking of doing. Now in the next video we'll talk about neutrinos and antineutrinos, and that's the final video ever. See ya.